네,
네.
안녕하세요.
네, 반갑습니다. 예, 문정이라고 합니다. 예,
안녕하세요. 전 노혜영입니다.
네. 어, 12시부터 시작하도록 하시죠.
네네, 그렇게.
네, 네.
제가 이따가 스크린 쉐어 하면 되는
아,
거죠?
예, 예. 잠시만요.
네.
제가 한번 해볼게요. 음, 지금 한번 해보시겠습니까?
네.
이번 정류장은 기숙사 상점입니다. 다음 정류장은 모천 강남입니다. This stop is Norwegian Canal.
스크린 쉐어 잘 되나요?
네, 잘 보입니다. 예.
네.
그 스탠포드 시빌 엔지니어링 한국 학생들 좀 있나요?
한국 학생들 좀 있는데 많지는 않아요.
네.
예, 보통 두세 명 정도 있었었는데 항상.
네. 중국 학생들이 많죠?
네?
중국 학생들이 많죠?
요즘에 중국 학생들 많더라고요. 더
어,
많아졌더라고요.
더 많아졌어요.
네.
그 교수님 발표 저희가 세미나는 1시간인데
네.
뭐 30분 정도 하셔도 되고 40분 정도 하셔도 되고
네.
뭐 학생들한테 질문도 있으면 뭐 질문도 받고 이렇게 진행을 하면 될 것 같습니다.
예. 하는 중간에 질문 있으시면 중간에 해주셔도
아,
좋고요.
네네.
네.
좋습니다.
그러니까 길이는 40분 약간 넘어갈 것 같긴 한데
아,
45분 정도 되려나?
네. 그 원래 이제 저희가 이거 BK 뉴 프론티어 세미나라고 해가지고
네.
저희가 이제 원래 외부 공개는 안 했었거든요.
네.
근데 그 송준호 교수님 이메일을 보니까 뭐 외부 공개해도 상관없다고 하셔가지고
예.
이거를 뭐 외부 공개라는 게 결국에는 저희 이제 BK 웹사이트가 있는데 거기에다가 뭐 유튜브 형식으로 올리는 정도로 해야 될 것 같거든요.
네.
괜찮으신가요? 뭐 저희는
예.
상관없긴 한데 네.
예. 저번에 송준호 교수님께서
네.
이렇게 퍼블릭ली 어베일러블 해도 되냐고 하셔서
아,
저는 네, 해도 상관없어요.
네,
없어요.
알겠습니다. 예.
네.
내용 좀 많이 줄여주시고요.
이게 주로 대학원생들
네, 그래서 제가 잠깐
하는
소개를
건가요?
드리면은
네.
저희가 이제 브레인 코리아라고 하는 그 한국 연구재단에서 하는 사업이 있거든요.
네.
그래서 전국에 이제 건설환경공학부에서 4팀 정도만 이제 4학교만 이 사업에 선정돼서 저희가 연구비를 받으면서 이제 학생들한테 서포트도 해주고 하고 있는데
그 부분을
저희가 그래서 이번에 지난 학기에도 BK 뉴 프론티어스 세미나라고 해서 이제 세계적인 석학이 되실 그런 잠재력이 있으신 분들이 또는 뭐 이미 세계적인 석학에 반열에 오르신 분들 저희가 추천을 해가지고 2주에 한 번씩 격주에 한 번씩 저희가 세미나를 하고 있습니다. 예. 그래서 대학 전부 다 대학원생이라고 보시면 될 것 같고 뭐 소리가 지금 딴 소리가 자꾸 들려서 그러는데 전부 다 이제 대학원생들이라고 보시면 되고요.
네.
그리고 이 세미나 같은 경우에는 저희가 브레인 코리아 뉴 프론티어스 세미나 겸 또 저희 학부에서 또 이번에 새롭게 세미나 과목들을 또 하고 있거든요. 그래서
네.
이제 레질리언트 인프라스트럭처 세미나 과목 수강생들도 있고, 그리고 이제 스마트
아, 네.
시티에 관련된 세미나 과목 수강생들도 이제 다 포함되어 있는 걸로 저는 이제 그렇게 알고 있습니다. 예.
아, 네.
네. 뭐 그럼 시간이 됐으니까 시작할까요?
아, 예.
네, 그럼 예, 안녕하세요. 저는 BK 저희 교육연구단의 부단장을 맡게 된 문주혁이라고 하고, 이번에 이제 저희 2학기에 여러 이제 연사들을 저희가 초청을 해가지고 이 뉴 프론티어스 세미나를 이제 하려고 합니다. 그래서 이번에 2학기에 이제 첫 번째 저희가 스탠포드의 노혜영 교수님을 모시고 Structures as Sensors 그의 타이틀을 가지고 저희가 세미나를 하는 시간을 갖도록 하겠습니다. 예, 모두 박수로 환영 부탁드립니다. 예.
예, 안녕하세요. 감사합니다. 저 세미나는 영어로 하겠습니다.
네,
네. Okay. Thanks for the introduction, everyone. So my name is Hae-young No. And let me actually share screen first. Is it working? Okay, let's see. So yeah, I'm Hae-young No from Stanford University. So today I'll talk about the concept called structures as sensors, which indirectly monitor humans and surrounding environment through the ambient structural responses like vibrations. So let's see. So these days, our daily life heavily depends on civil infrastructure systems like buildings, bridges, or various transportation systems. And we're continuously interacting with these infrastructure systems, large-scale physical systems. So we have to think, what if these structures become smarter? By making the structure smarter, we can sense different kind of potential failures in the structure to prevent catastrophic events and reduce accidents. So we can increase the safety of these structural systems. But in addition, by better understanding the occupants using these structures or the surrounding environment, we can provide better services like personalized cares, enhanced health care for people, or security systems, or better preserve the environment around these infrastructure systems. So to make these structures smarter, one thing we need is the sensors to collect information about this infrastructure and people. Right? So we can put sensors on the infrastructures, or we can put cameras around to watch people and like various occupancy sensors and so on. So you see, this is what we need. Just need to have a lot of sensors to collect information. But then this sensing in the infrastructure system is actually not a very easy task. There are several reasons for it. One thing is these structures tend to be very large in scale and also very complex. So in order to instrument all these large scale structures, the system gets pretty expensive. Another thing is the sensor life tend to be short. It's relative thing. So you guys know what's the typical sensor lifetime? Anyone? So easy example would be, think about how often you change your cell phone. Maybe 2 years. Or if you are better maintaining your phones, maybe 5 years. But I wouldn't put more than 10 years. So that's the scale for sensors. Then think about the infrastructures, the buildings and bridges that we're designing. They're designed to last for at least 50 years or 100 years. Sometimes they're standing out there for thousands of years. So there's a huge gap between the lifespan of these sensors and the infrastructure systems, meaning we will probably need frequent updating of the systems and the software and so on. So that will make the system even more expensive. And then if you want to do more complex analysis of people and environment and structure together, we need many different types of sensors, which will make the system even more expensive. So in this regard, my research group has been focusing on answering the research question of how can we sense all these things in a more maintainable and sustainable way? And as an answer to that, we proposed the idea called the structures as sensors. So what it means is, let me give you an example. So typically, if you think of the sensors, the physical component of a sensor in for example, the microphone, is considered a small diaphragm inside a microphone that vibrates as the sound wave comes in. So it's responding to the input, therefore it generates the data that correspond to the incoming sound wave. But now, instead of thinking of this small diaphragm, we're gonna think of this entire building structures as a sensor, physical component of the sensor that responds to the input coming from the humans and environment and the structures, so it can collect information about them. So this idea is based on the insight that if you look at these structures, like the transportation systems or the buildings, their structural responses, like their vibrations, depends on the structural conditions themselves, like whether they're intact or if there's any damage to it, that all gets reflected to how these structures move. But they're also sensitive to any activities ongoing for the occupants that are using these structures. And also, of course, they're affected by the surrounding environmental conditions. So by looking at how these structures respond to all these input information, we can acquire the data from it and then extract useful features out of it, put it into the learning models, and then we can extract information about the sensing targets like human activities, structural damage, and many surrounding events around the structures. So looks like problem solved. We can use these humongous sensors to collect all this information in an easier way. But then we found out that in order to enable this structures as sensors approach, we actually need a lot of data. That's because I just explained that structural responses has all these informations about human structures and environment, which is awesome. But in order to extract the desired information that you need, you actually need to decompose all these. All the other information that you don't need are going to become the noise, and you only want to extract the target information you want. So in order to do that, you need a lot of data samples in order to understand this complex mixture of multiple sources of excitation. Another reason will be every structure is unique. Do you think of the buildings? Every building look different. And even if they are designed same way, they're constructed differently and they're also used and operated in a different way. So they become different structures over time. So in order to understand these individual structure responses, we need even more data, good data. And then many of the interesting events that we want to detect or predict tend to happen rarely. Like structural damage, how many times do bridges collapse? Very small amount compared to all the other healthy bridges out there. So same thing, how many people get sick compared to all the healthy people out there. So in order to capture all these rare events, we need seriously more amount of data. Okay, so it looks like we just need to use structures as sensors approach and just collect a lot of data. Problem solved. But it turns out that getting real data is actually a pretty hard task. Let me give you an example. Like the picture shown here is actually my PhD students and me collecting bridge data. We're doing the structural health monitoring of this railway bridge in Pittsburgh. And we were allowed to collect data only between 1 a.m. and 6 a.m. because that's when the trains are not running on these bridges. And so we went out, collected the data for 3 nights, and all we got was 20 samples for 3 different states of bridge. So 60 sample data. That's a lot of field data, but if you think about it, 60 samples is a very small amount of data in this era of big data. Right? So imagine trying to damage the bridge 1,000 times in all different temperatures, traffic conditions, and different levels of damage. It's gonna be very time consuming and expensive. How about asking a person to walk around in the building 1,000 times in different speed, wearing different shoes? What if that person's your grandma? You definitely don't want to ask her to do that. So this high dimensional complex problem with scarce data is a fundamental challenge that we have to deal with when developing or using machine learning or data analytics in the real physical world systems. So in addition to the first research question I posed about how do we sense everything in a sustainable way, the second research question we've been working on is how can we understand the output of the structures as sensor system with minimal data requirement. And in this regard, we've been developing our physics-guided learning approach. So here's the framework I introduced earlier to show the structures as sensors idea. So here, in addition to the data we're collecting from the structures, we're going to combine the structural response models that explains how these structures respond to different kind of excitations, how the wave propagates inside, so mechanics and dynamics and vibrations and so on. The structural response models, and also the sensing target models. How do people usually behave? What's the environmental properties? How do they vary over time? How do they affect the structures and so on? So all these different components are informed or guided by the physical knowledge or the domain expertise from our engineers. And all these models are going to be combined as a physics-guided learning approach. And then through this learning approach, we extract the sensing target information, which in turn will be fed back and used to improve the state of the sensing target, so improve people's health condition, improve the structural health condition, or improve the data acquisition system. Okay. So for the rest of this talk, I'm going to show you examples of these structures as sensors and physics-guided learning approaches. The first example will be using this transportation system as a sensing system. So in particular, I'll be using the trains as sensors to monitor the track and bridge health. So maintaining rail tracks, the current practice of maintenance heavily involves the human reporting. Usually the drivers will be driving these trains, and if they see anything or if something doesn't feel right when they're driving, they call the maintenance department and tell them to go fix it or just go out and take a look. So, or there are like a regular every other year, they send out a couple of trained engineers who will walk on these tracks and visually inspect to find any faults. And as you can imagine, there are like thousands of miles of rail tracks out there. So it's very labor intensive, costly, time consuming, and also subjective because it's human work. So to address these issues, research communities have been developing various sensing systems to directly monitor these rail systems, or non-destructive evaluation methods that they go out and install the sensors on the rail network, or they build a specialized trains with all these laser scanners and ultrasound, all these equipment in there, and these bogies can run in quiet times to inspect the rail. But given the scale of the infrastructure, you can imagine that this is still pretty expensive to both install and maintain. So to that regards, our group has proposed a solution. This. So if you think about it, these regular operational trains will travel across the country using these rail tracks every day, or sometimes multiple times a day. So why don't we make these vehicles smarter so we can use them as sensors? So we can diagnose damage on the roads, railways, or railway bridges using only the onboard sensing system in these operational vehicles. So as these instrumented vehicles are traveling across the rail network, it's continuously collecting the information and send it to the classification system. And if any anomalies are detected or any defects are detected, the information can be sent to the transportation authority, who can send out more people to further inspect it and repair if necessary. Okay. So looks like problem solved. However, there's never free lunch. So we identified several interesting research questions. So the major thing is these train vibrations, the train responses we're sensing depend on the infrastructure conditions, like the track roughness that we want to sense, as well as the other things like the operational conditions, how fast is the driver running the train, or the train properties, the mass and stiffness. Like if you think about the rush hour versus quiet hours, the number of passengers will change, which will change the mass of the train. And also the suspension system may wear out over time, so that would change the stiffness of this the trains. So all these factors we have to consider, and if we're trying to model all these variations and trying to analyze the data, it's almost impossible. Like I have a very simplified version of the model down here, so we can use the track profile or track status as the input, which is put into the system, which is the vehicle dynamic system. And the output is the vehicle response, which is a combination of the track profile and the vehicle system. And what we want to do is the track profiles are known, vehicle systems are known, and we want to infer these unknowns based on the sense data vehicle response. But since there are too many unknowns, it's a heavily or highly ill-posed inverse problem. So we need to introduce more constraints to it. So I made several observations to address this issue. The first one was the train suspension is mostly activated by a few major bumps that naturally exist in the rail system, like joints and switch gears. Also, the unnatural bumps, like the defects that we want to detect. So based on this observation, we can impose the signal sparsity in the track profile we're going to infer. Okay. And the next observation we made is that the train's fundamental mode tend to dominate the overall dynamic response that we've been collecting. So we can simplify the train dynamics model in our overall modeling. So from this, we actually simplified it down to the single degree of freedom system to represent the train dynamics. So we put these approximations together to formulate the problem to estimate the track profile or track damage state. And it became a whole optimization problem. I won't go into the details of the mathematics here due to the time limitations, but basically what we're trying to do is we're trying to minimize the discrepancy between the train response, the measurement U, and our model prediction. Here H times R represented here, subjected to a couple of constraints that I mentioned above. Okay. And solving this also doesn't have a closed form solution, so we had to develop another iterative machine learning algorithms in order to infer the track profile out of this optimization method. Okay. So all the methods are developed, but no one's gonna believe if it's gonna work unless we show the proof for it. So we did an evaluation. So this evaluation was done with the collaboration through the collaboration with the Port Authority of Allegheny County and Pittsburgh. So we instrumented a couple of trains in Pittsburgh, the light rail trains in Pittsburgh. So we deployed in 2013, and it's been continuously running since then. We only have 6 years of data because the instrumentation the data collection kind of stopped at the beginning of 2020. You can imagine why that happened. Our students couldn't travel to Pittsburgh anymore to retrieve the data. So anyway, we've been continuously collecting the train response data since 2013. And if any of you are interested, we actually open source the data set you can use this DOI and the link to download the data if you're interested in taking a look at the data or developing your own methods. Okay. Just to show you the scale of the deployment, this is the 2x9 kilometer Google map with the train trajectory on top of it. Okay. So let me show you the quick results. So this figure shows the raw signals of the train vibration response we collected from 145 different passes going through the same 50-meter segments of the track. And it's very noisy. There are 145 different passes that we need to compare in order to detect any changes happening in the track. However, it seems almost impossible to do that. It's too noisy and they're not really comparable. So after applying our sparse approximation and signal alignment methods, here's the results. So now most of the noise is gone and the signals look a lot, they look alike each other a lot more than before. So now it's feasible to make a comparison between them and run the detection algorithm to detect any anomaly in the track geometry from these features. Okay. So just as a summary, we were able to extract these track profile features by combining the machine learning algorithm with the physics-based model. And we were able to reduce the feature dimension by 100,000 times and was able to remove most of the noise that's existing in the data set. And using these features, we were able to identify the damage with about 92% accuracy. And because the features based on the physics-based model, we were able to also make an interpretation, and I was able to locate and quantify the track changes that's happening there based on the feature value. And it was robust to different train conditions like the mass or stiffness, or different operational conditions like the running speed of the train. Okay. So that was the first example. And just to show you the generalizability of this approach, I'm going to talk about the second example, which uses the building structure as the sensors. So if you think about the building vibration, a lot of structural engineers use these building vibrations because it contains a lot of information about the dynamic characteristics of the structure and also the input excitation. And it's commonly used in structural health monitoring to diagnose damage or do prognosis, or even do the serviceability analysis to make sure that people feel comfortable inside the buildings. Okay. But then we realized that it's not just the structural information that the structural vibration, building vibration contains, but also the human information. So when people have physical activities in the building, their physical motions, for example, the footsteps, creates vibration on the floor that will propagate through the whole structure. So building vibrations are caused by human activities, human motions. So this way we can sense humans through structures, and it actually has various benefits compared to other ways of sensing human activities. So there's definitely no need to carry a device for people. So it's non-intrusive and minimal interference to the regular activity of the people. And there's much less perceived privacy concern compared to other sensors like cameras or microphones to track people. So let me show you an example of what the data would look like. So this is an example of the vertical building vibration measured using the geoform when people are walking by. So x-axis shows the time, y-axis shows the vertical velocity of the floor structure. And you see each impulses here correspond to each footstep of a person. And as the person's walking towards the sensor, you see the amplitude going up, and as the person passes by the sensor and go away from it, you see the amplitude going down. So by putting several of these data acquisition systems and geophone sensors on the floor, if the footstep happens or if human activity happens, that's going to create a wave that will propagate and hit the sensors at different time with different waveforms. So by combining these different waveforms together, we can figure out who you are, where you are, what kind of activities you are doing, what's your health status, or even sometimes the cognitive status of some of the occupants. So here's a video showing the real-time data collection we've done. The top figure shows the time domain signal. The bottom colorful figure shows the frequency response, frequency spectrum of the signal. And the red boxes means our system has detected that signal as the human footstep induced signal on it. So once we detect the footsteps in the signals, detecting and recognizing or classifying it as human-induced footstep versus all the other impulses like door slamming, someone dropping an object, that's a pretty straightforward classification problem. So we can easily do it with accuracy of 99.5%. Okay, and once we extract these human-induced signal, there are various characterization of the occupants we can do. So one of the characterizations we're able to do is identifying people. So everyone walks differently. It's a known fact in the medical domain because all of us have different bone structures, different muscle structures, our brain wired differently. So people have unique gait patterns. I have examples of two students walking here. On the left-hand side is our PhD student, Carlos. On the right-hand side is our master's student, Ningning. So Carlos, the PhD student, this data was taken like just before his graduation. So he's busy with paper deadlines, professors calling him for meetings. So he's always kind of in a hurry. Whereas Ningning was our master's student. When the data was taken, this was like after she got her job offer and was after the final exam. So she's very relaxed. And also she's a pretty laid back person. So if you look at the way they walk, you see that Carlos his motion is more forward motion. The center of gravity is kept at the center or a little forward, whereas Ningning's center of gravity tend to be kept in the back. And that creates a difference in how the foot hits the floor. So Carlos has smaller angle than Ningning between the foot and the floor. So Ningning having a larger angle between foot and floor end up having more like a stomping kind of action when she's walking. And of course, all these differences in the way they walk, it's reflected into the data we're collecting. So here, top rows correspond to Carlos's data. Bottom rows correspond to Ningning's data. And the first column represents the time domain signal. Second column corresponds to the frequency domain signal. And the biggest difference you see is Ningning tend to have stomping action. So it's more like an impulse, like excitation to the floor. So you see that her signal has a large peak that decays fast. Whereas Carlos has a smoother kind of contact with the floor, so his signal tend to decay a lot slower. And of course, there are different peaks and valleys in the frequency domain responses. So we extract all these as a feature and put it into the learning algorithm to classify whose signal it is. So we extended the data set to 10 different people, collected 10 different traces per person, and the results are shown in the middle plot here. So x-axis shows the number of traces that we use for training. So of course, if we use more data for training, the accuracy goes up. So y-axis is the accuracy. So here, the blue line corresponds to the step level accuracy, meaning every single footstep we try to identify a person, and we got up to 90% accuracy. The orange line, however, is the trace level classification because no one will have just single footstep and disappear, fly away. So people usually have several consecutive footsteps showing up together. So using that fact, we will gather several consecutive footsteps, group them together, and try to identify based on multiple footsteps together. And we got up to 99% accuracy for identifying people. So our PhD students got pretty excited. Now we can publish this. So they were excited. But then I said, oh, let's do one more test. Like, let's go to the upstairs and see if it still works. And then we found out that on a different floor, the accuracy suddenly dropped to 20%. So it's like students all depressed, like, oh, what's happening? So it turns out that, of course, the signal we're collecting is a structural vibration, whereas we're sensing these people through the structure. So if we move from one structure to a different structure, or even from one location to a different location within the same building, if the underlying structure is different, the signal will be different. So you can see that in wooden structure, concrete, or the metal, the steel structure, even with the same excitation source, the data we collected will have different distributions. And we went back and we checked whether the detection will work well. Even the detection accuracy went down to 63%. So we can't even tell whether it's a footstep or other kind of impulses accurately anymore. So this is a significant drawback in the practicality of the method, because this means we need to calibrate or collect new training data set in every single structure. So instead of requiring that, we went back to our ideas and thought about, can we actually reduce this data requirement by bringing in more domain knowledge and reformulating our learning algorithm? So I'll introduce the new method we developed to address this problem. So it's basically trying to transfer the model using the structural properties that we know. So our solution is we're going to extract a smaller set of label data from a few number of source structures, a few number of reference structures that we call the source domain structures. And then we're going to transfer the model based on our knowledge about the source structure and the new target structure that we want to test our system on. So that we can still have higher accuracy without requiring the labeled data collection from these new target structures. So the basic idea is, here's if you collect the data from the human footstep versus all the other kind of excitation, that you're gonna end up with two different data distributions. So the difference between these two distributions, we call it excitation effect, because they're due to the different excitation sources. And all these data together will belong to the source structure data. And if we move to a different structure and collect the same kind of human-induced versus other kind of excitation responses, then we're gonna end up with a different data set, the green blob shown, the gray blob shown here. And there's going to be a difference between the source structure data and the target structure data distribution. And the discrepancy between them, we're going to call it structure effect. Okay. So now the idea is, can we transform this feature space we have, the original feature space, to some other space such that these two blobs, the orange blob and the gray blobs, are overlapping each other? Basically, can we transform the feature space such that we minimize the structural effect? So finding this projection matrix W. So this can be formulated into, again, the optimization problem. So I won't go into the details again, but it's basically trying to find the W, the transformation function, that minimizes the structural effect, the distance between the two distributions, also with the regularization term to make it robust to different noise conditions. And we also had a distribution shape preserving term, because without this, the answer is going to converge to like trivial solution, multiply everything to 0, then all the data will overlap. And then, of course, we have the label information, so that data with different labels, like human versus non-human excitation, the data are still separable in the new space. Okay. So by solving this optimization problem, we can come up with the transformation matrix W, and then we can transfer the model to the new structure for the target structure. So we evaluated this method through 3 different structures. One is the campus building. That's a non-carpeted concrete slab on grade kind of floor structure. Second one is a nursing home that has carpeted metal deck floor. And then the third one is another nursing home that has carpeted wooden floor. And the results is shown here. So there are 3 groups. Each group, the x-axis shows the building name, Baptist, Porter, and Vincentian, meaning the Baptist means the Baptist building is used as a test, the target structure, and the other 2 are used as the source structure. And same for the Porter and Vincentian. And you see the green bar, which is the result of our approach, has a lot higher accuracy or F1 score compared to the other 2 methods that doesn't incorporate the model transfer. Okay. So now looks great. So what can we do with it? What further things can we understand using this kind of method? So I just showed the results of person identification. We were able to identify different individuals with up to 99% accuracy, and we developed an iterative learning algorithm to make this robust to different walking speed. We were also able to localize the occupant, individual occupant with up to 0.2 meter accuracy. And if you think about it, we're localizing the footsteps. So it'll be pretty difficult to go get accuracy that's smaller than your foot size. So 20 centimeters is a pretty good accuracy here. We were also able to count when there are multiple people walking together and locate individuals separately. And we also showed that the localization method works even with the presence of obstacles like walls or furniture in between. And we've been also working on characterizing other aspects like identifying different types of activities like cleaning, vacuuming, or cooking, writing, talking, typing, and so on. We've been also working on characterizing the health status of the people, like what is your gait balance, how far can you walk, what's the tiredness, and so on. And from these, we're able to achieve above 90% accuracy. And currently, we're working on extracting more sophisticated gait parameters that are closely related to different types of disease of people. Okay. So let me show you one like a field deployment with it. We've been working with the Nationwide Children's Hospital and the Amish community to monitor patients who have muscular dystrophy. So muscular dystrophy is one of a neuromuscular disease. So typically when you guys go out and exercise, it hurts next day, right? That's because your muscle has muscle fiber broke. But then it's gonna rebuild soon, and that's how you get your muscle gets bigger and you get stronger. But if you have this muscular dystrophy, your muscle does not regenerate. So these kids, little kids with this genetic disease, will start with losing the leg muscle first because that's the muscle they use a lot, and then eventually they lose the respiratory muscles, so you can't breathe anymore, and that's the end of the life. So their life expectancy is about 20 years old. It's a genetic disease and often shown among the boys in Amish community because they tend to be a smaller and closed society. So what we've been working with the medical doctors in the Children's Hospital is trying to understand the patient's disease status through their gait patterns. Because when they lose the leg muscle, the changes in their gait pattern is one of the early symptoms of the disease. And if they detect the disease early on and put it into the right gene therapy and so on, their life expectancy grow by 50%. The expected lifetime is about 30 years old. So this can be a huge help for these children. So we're trying to extract their walking ability, the walking speed, whether they have regular heel toe motion when they walk, they have the right ground reaction forces, tiredness, what's their force balance when they're walking, and so on, and then correlated it to the disease progress, the medications they're taking, and different fall hazard they have. So this is a nice way of informing the doctors and caregivers in a continuous way the patient's health status. Otherwise, these kids will go to see the doctors every month, whereas this system will update the doctors about patient status every day or even every hour. So here's a quick result. When we use just a symptom-based, physics-based feature, we were able to achieve up to 86% accuracy in terms of detecting whether it's a data from a patient or it's a healthy subject. If we combine all these features, we can achieve up to 90% accuracy. If we use purely data-driven signal-based feature, that's 83% accuracy. But by combining this physics-based and the data-driven approach together, we were able to achieve 88% accuracy. And then if we remove the structural effect, then we were able to get 96% accuracy in terms of detecting the disease. So this is one example of how we can utilize our system in the real life. There are several other real-world projects we have. We've been working with the USDA to do animal monitoring. Apparently, kids are pretty similar to pigs in terms of the activity. So we're sensing the ground vibration induced by the animals, in this case, the pigs, to figure out what kind of activities they're doing. Do they have any fights? Are they sick? How often are they eating? Are the mother pigs taking good care of the baby piglets and so on? So we correlate those data to animal health. Another thing is human health. We've been working with the elder care centers to do the activity monitoring of the elderly patients with Alzheimer's or other like a Parkinson's disease and so on. And we're also looking at the fall hazard, because falls can be pretty detrimental for the elderly residents or the patients. The hospital president that we work with mentioned that when the elderly patient falls, about 1/3 of them are fine, but another 1/3 will have severe injury from it, and another 1/3 will actually die from these falls. So it's a pretty severe, important problem. So we are looking at different gait patterns that is an indicator of the fall hazard, so we can give them a warning and make them take more breaks between the walks. And another example of the project is looking at human activities. Here I have an example of hand washing. So when you turn on the water runs through the pipe, that also vibrates the structure. And if you're rubbing your hand under the water, that also creates different kind of vibration. And when you walk towards the sink, walk away from the sink, we can detect who's there and how much time they spend washing hands, or if they use the soap. So in summary, so far I talked about the first topic of how can we sense everything, and we introduced the idea of structures as sensors. And I also talked about how we can understand the output, very noisy output coming from the structures as sensors with minimal data requirement. We address this problem through the physics-guided learning approaches. So before I finish, I would like to acknowledge and thank all my students. This is actually a lot of hard work done by my PhD students, although I've been taking all the credit by making the presentation here, and also the funders and the deployment partners. And also there are a lot of collaborators from various disciplines and also from government and industry. Okay. So that's it. Thank you, everyone. And let me know if you have any questions.
Thank you very much, Professor No. It's very, very impressive presentation. I think students can have a very good opportunity to know the example and the future application of the structural dynamics. So any questions from students first? 한국말로 질문하셔도 됩니다.
Hello, can you hear me?
Okay, yes.
Okay. Hello, Professor. First of all, thank the professor for introducing a lot of very interesting research. I see very interesting research, and I am very interested in identify people work differently. You pass the signal to receive the pedestrians working angle and like working frequency to identify who it is. The accuracy of defining a person has reached the 99% to define a person. Can it be used as a person's ID card in the future? Is it feasible? And for example, at the train station and waiting for places that require identification, for some high-end apartments are registering laboratory to prevent outsiders from entering. For example, like this is the question. Thank you.
Okay, yeah, sure. I'll say short answer is yes, but there will be situations that this system will work better than the others. So in certain situations where people are like people have to line up and enter, for example, it will work really well. If there's certain expected people that we have database for, then we can also identify them pretty accurately. If there are 100 people marching together, for example, then it will be very difficult to identify them. So in that case, instead of identifying individuals, the system will switch to more like overall activity level monitoring. We do have person identification methods when multiple people are walking together. We look at the scale of like about 4 to 5 people walking together, and that's been done. We didn't go beyond that because usually like in behavioral science, when like there are 10 or 20 people walking together, they usually don't walk all together and like marching like a band. They tend to usually break down into small groups of 3, 4 people, and then they'll be chatting and walking together. So that's why we targeted that more common scenarios. And if there are multiple groups and they tend to be a little further away from each other, then there will be a different set of sensors trying to target different groups. So the nearest sensor group will try to detect them. So that's how we target when there are a large number of people walking together in a general direction.
Thank you, Professor.
Any other questions?
I have a question.
Yeah.
Yeah, thank you for your lecture. In the third page, you showed various kinds of infrastructure, or what kind of smart infrastructure can be helpful for our daily life. But my question is, what is your research or your technology can be applied to environmental monitoring?
The environmental monitoring we've been doing is, so I call this surrounding environment. So when we use the cars as the sensors or the train as the sensor, like surrounding like an infrastructure system that they're utilizing, it is considered as one of the surroundings or the environment. There's another thing, we actually deployed air quality sensors and environmental sensors in these vehicles as well. So that's not exactly using the structural vibrations itself, but the cars are acting as the sensing medium to as a sensing vehicle to sense the actual environment, the conditions within the city, like the temperature and the air quality and so on. Another environmental effect is by looking at these train vibrations or building vibration, we can actually look at the signal trend changing with the temperature outside, and the signal trend, like a frequency spectrum changing with the temperature, and also it changing with whether it has rained or not, because the water tend to change the foundation condition, which changes the building, the structure and the foundation, the interaction, soil structure interaction between them. So it's reflected in the structural vibration as well. So that counts as another environmental condition. And then other thing is, if there's from the building vibration, we're able to detect the traffic outside. So when there's a train passing by or a heavy truck passing by, the building actually responds to it. Or if there's a heavy construction event, it can also pick it up. So that's another environmental or the surrounding events that the structures can pick up.
Thank you.
Any other questions? So before we end, I'd like to ask a couple of questions because it's very impressive to see, because most of the structural engineers in civil engineering, they are focusing on the evaluation and rehabilitation of the structure itself. So I have seen piezoelectric energy generation from the vibration of structures, or structural health monitoring, but I actually haven't seen this kind of application, such as a people identification, or even the health status of the people inside of structure. So Professor No, I want to know the pros and cons of this new kind of structures as a sensors compared to other sensing systems. For example, cell phone, we may be able to get more data easily, but what do you think about the future direction, and what is the big advantage of this kind of technology compared to the existing sensor systems?
The biggest advantage of this system will be it's all infrastructure based, so it's non-intrusive. We don't require people to wear anything or carry any device, which is especially useful for healthcare applications, because patients don't want to wear anything. It's like when we work with the Alzheimer patients, we have to say, Grandma, if you only remember to carry this device and charge it and update it, then we can help with your Alzheimer. But these are Alzheimer patients, so it's very beneficial when we're working with people where the wearable is hard to manage. Also, if it's in open space, like in a in a private home, it's easier to control. Like, you know how many people are living there, who are the frequent people who show up in the area. But if it's like a shopping mall that like unknown people, anyone can come in, then you cannot really require them to wear anything or carry anything, carry cell phone and so on. It's a lot less sensitive in terms of privacy compared to those camera systems or the voice recording systems to track, identify people or locate the people. The accuracy is surprisingly a lot higher than many of the like a Wi-Fi based or Bluetooth based people tracking devices. So those are the major benefits of this system compared to other sensing systems. So, and in the future direction, I see that it will be like, in order to commercialize or being widely used, it will be nice to use a combination of the different sensing modality. Like, for example, in public space where putting a camera is okay, adding a camera in addition to this vibration sensing will further enhance the accuracy, definitely. But you definitely don't want to put camera in the bathroom or the bedroom of the people, then this vibration can track it very well. In a place where there's a lot of people, like very crowded, like in a big train station, then like if we can also utilize the cell phone data, that will give a more accurate counting of the people or the identity of the people. Yeah, so I think future direction will be fusion of many of different sensing modality.
Thank you, Professor No. Do you have any other questions before we finish our first New Frontiers seminar?
I have one question to Professor No. Yes. Thank you very much for your wonderful presentation. So personally, I'm interested in the system identification and the parent detection. Can you show us the other slide on page 19 or 20 about your light ray train?
19 and 20.
Yeah.
Okay. 19.
Oh yeah, here. Yeah. So you mentioned that you were able to detect the track change of the rail with the 92% accuracy. So generally, structural properties are affected by the temperature change. So even if we apply the same load to structural grades, but the response of the structure may be different in the morning or in the afternoon, depending on the temperature change. So how were you able to remove the effect of the temperature change for your system identification?
Yeah, that's a very good point. And we actually plotted the frequency spectrum and the frequency domain-based features as a function of temperature. Because we have 6 years of data, we got a huge variation of the temperature, and it actually showed a linear trend between the feature we extracted and the temperature. So the normalization to some degree was able to play some role to mitigate the temperature effect. It didn't completely get rid of the temperature effect. And another benefit we had is it was a real rail track system. So we couldn't really induce the real damage to the track. So what we did was we look at the inspection reports. And when there was a damage, they do the inspection and repair during the summer when there's no snow. So we pick out those damage cases, look at the signal like a month before the damage happened, and then after the repair is done, and trying to see if we can actually detect that change. So it is true that a lot of the sample data we had was taken in summer, which had temperature variation, but not as much as the winter and summer variation. So that was another factor that played in.
So it sounds like in order to apply this kind of method, we also need to have some kind of some background data related to temperature change, or so in order to extract some meaningful features. And it sounds like we need to have some good background data so that we can effectively remove the
definitely
feature.
Yeah, definitely. And that's why this kind of long-term monitoring data is very useful, because it allows us to look at the whole trend with different weather conditions and the aging of the train system itself. And in the middle, they actually changed the wheels in the train, which changed the train response as well. So it's nice to explore the real world data that's been taken for a long term.
Okay, thank you.
Yep, thank you.
네, 발표 감사드리고 질문도 감사드립니다. 시작을 한국말로 해가지고 끝나는 것도 한국말로 해야지 좀 할 것 같습니다. 네, 일단 그 밤 시간일 텐데 좋은 발표 해주셔서 너무너무 감사드리고요. 다음에 또 좋은 기회가 있으면 뵈면 좋을 것 같습니다. 자, 좋은 발표 해주신 노영 교수님께 박수 한번 드리면서 저희 첫 번째 BK New Frontier 세미나 마치도록 하겠습니다. 감사합니다.
네, 감사합니다. 저 초대해 주셔서 감사하고요.
네.
예, 다음에 또 기회 되면은 이제 직접 인퍼슨으로 한번 만나뵈면 좋을 것 같습니다.
네, 좋습니다.
감사합니다.
네,
감사합니다.
여기까지 하겠습니다. 감사합니다.
네.